we can get additional performance by assuming that sets are ordered sequences. So here's a second proposal. A set is represented by a linked list with unique elements as before, but this time they're in order, from least to greatest. But I just said that sets are unordered collections. What does it mean for it to be ordered, but unordered at the same time? Well, the answer is in abstraction barriers. So parts of the program that use sets to contain values. Assume that sets are unordered collections, which means that even though they might be in order, we're never going to assume that fact, which allows us to change our representation from an unordered version to an ordered version whenever we decide to. We manipulate sets using empty or set contains or a join set or intersect set. Then there's the part that actually implements these set operations. That is going to assume that every set is an ordered linked list. It's going to assume the ordering only for the purpose of efficiency. And it's going to use first and rest attributes and less than and greater than and equal to compare the different elements, and thereby implement intersect and union and all the others. This abstraction barrier separates the parts of the program that make fewer assumptions about sets and the ones that make more. So, if we build our program today, and then tomorrow, think of an even better way to represent sets, the parts that do implementations of set operations are all going to have to change. But the parts that just use sets won't have to change at all, because they never made any assumptions about the ordering. So the powerful idea of the day here is that different parts of a program can make different assumptions about data by respecting abstraction barriers. Okay, now what actually changes in the implementation? Well, intersection becomes much faster. We define intersect set between two sets, which we're now assuming are linked lists that are ordered from least to greatest. The intersection, if either is empty, is an empty set. Otherwise, we look at the first two elements, the first element of set 1 and the first element of set 2, and we call those E1 and E2. If they're the same, then that value, E1, is in the intersection. And so we return a linked list that contains that element and the intersection of the rest of both of the lists. Now we know that this will be ordered as well, because E1 and E2 were the smallest elements in their respective sets, and so they have to be smaller than anything in the intersection of set1.rest and set2.rest. What if E1 is less than E2? Well, then we call intersect set on the rest of set 1 and set 2. What's going on there? Well, if E1 is less than E2, then we actually know E1 isn't anywhere in set 2, because it's less than the smallest element in E2, so it has to be less than everything else. And if it's less than everything else, then it's not equal to anything else. So that means we can throw away E1. We haven't gotten rid of E2 yet, so we're passing in all of set 2, because it might be that's somewhere in set1.rest. If E2 is less than E1, which is the only other possibility here, then we keep E1 as part of set 1, but we throw away E2, keeping only set2.rest, because we know it doesn't appear anywhere in set 1. Now this implementation of intersection is actually a lower order of growth than the intersection algorithm we had before. This is theta n, where n is the size of a set. Because the size of the sets together is just 2 times n, and we're making progress in at least one of the sets each time, sometimes both. So we're going to take on the order of a linear number of steps in order to process both sets together. And we can only do this because we're taking advantage of the ordering for the implementation.